can be very poetic what we do, right? We do things like weaving fabric. We've done it for thousands of years. And then we start thinking about the process and sort of quantifying that process, ordering that process. So I want you to look at your shirt sleeve. Okay? So if I look at my shirt sleeve, right here, it's a black shirt, and my eyes are old, and I don't necessarily have the ability to see what I want to see anymore. But if you look carefully at fabric, cloth, you see there's a thread, and another thread, and another thread. And the way this process, the way cloth is woven, is that these threads are interwoven, and I'm not going to worry about their intersections. I'm not as concerned about their intersections, but you know that every second thread is separated, lifted, and then you run a thread through the middle, and then you reorder those, right? And so it's always catching. But ignoring their intersections, whether one is up or one is below or one is above the previous thread, we have these threads. And you can create a fabric that way, right? And you can lie it flat, and it's just a plane, for example. And now you know, hey, I know about planes. Professor taught me a bit about planes, okay? But of course, you can take that fabric and you can move it up to some other point, a bunch of other points in space, right? The threads remain the same. Those are still the same threads, right? Those threads are doing this. Let's imagine we hold it there, we fix it there. Like my shirt's like there, right? It used to be a flat fabric, and now it's wrapped around my arm, okay? So there's an origin of coordinates somewhere, okay? That's where I measure everything from. And then I say, look, there's a point on this surface, which is my sleeve, or any other surface that I care about. There's a point on that surface. And if I can tell you what thread you're on and what cross thread you're on, if I fix that surface, that uniquely specifies where you are, where that point is. Does that make sense? Know the thread, know the cross thread. So if you think about it, to know where points on a surface are, you have to know where those cross threads are, those threads and their cross threads. And this is what we mean by parametrization of a surface. Okay? You can think of this differently also. You can think of these as roads. Another useful way to think of them is roads. A street, B street, C street, D street versus first, second, third, fourth, all the way up. Right? And they intersect, but where they intersect is a point in R3. It's a location in R3 because the Earth is, we are in a three-dimensional space, right? So those points are in R3. Okay? So these could be roads. These could be threads. And you have a label for them. If they're roads, you can say A street, B street, C street. First street, second street, third street. But of course, mathematically, we'd like to label them with a continuous parameter, right? And so what we would say is this would be the first thread. This would be the second thread. This would be the third thread. This would be the first cross thread. This would be the second cross thread. This would be the third cross thread. But of course, we go a step farther mathematically. We recognize that, OK, I've done a discrete kind of chopping of this space, but really there is the 1.5 thread and the 1.75 thread, and there's a continuum of possible locations along here. Okay? So if you want to find a point here, you say, oh, the location of this point, so there's my origin of coordinates. Now I'm going to draw it over here, make it a little bigger. So I create an origin of coordinates, a coordinate system. This is going to be x, this is going to be y, this is going to be z. Or put differently, that's the I hat, that's the j hat, and that's the k hat direction. And I have some surface in this space. Here's the surface. Okay? And I've woven that surface by a bunch of threads. Okay? And I want to identify this surface as the collection of points on that surface. So I have a vector, and this, draw it parallel. That's not very useful. Let me draw this one right here to that point right there. That's supposed to be straight, okay? That's a point on the surface. That's an R. And it's located at the intersection of two threads. Okay? And so you consider this as parametrized by two parameters, u and v. Okay? Why? Well, think of this thread over here. Let's just think of this thread over here. This thread is a curve. This thread is a curve, right? One can imagine that this thread is hold v fixed, and then you have a curve r of u at fixed v. And that's a curve that goes over here. Whereas, what is this thread? This thread says hold u fixed, and then you have another curve r of v. We understand that curves can be parameterized by one parameter. So it is plausible when you think of surfaces as a collection of intersections of curves that they're parameterized by these two parameters. Okay? So let me give you an example of how you parameterize a surface. Example. Okay? I'm going to be working a lot with the hemisphere or the sphere. Why? The sphere is one very important shape. Okay? We bump into it a lot. Not literally, but at least mathematically. So let's work with the sphere. And so my example is going to be the hemisphere, the hemisphere in z greater than or equal to 0 of radius capital R. And you all know by now that we can write the sphere as x squared plus y squared plus z squared equals r squared, and then we add this condition z greater than or equal to 0. So this is an inequality, and this is an equality. You have three variables. Remember, r is a given number, okay? It's a fixed number, 7. Okay? You have three variables. You put one constraint on them, so you had a three-dimensional space. You put one constraint on it. Generically, it's going to create a two-dimensional thing. That's the upper hemisphere, okay? If we want to write it explicitly, we write z equals the positive square root of r squared minus x squared minus y squared. That's an explicit version of this. That's an explicit version of this hemisphere, okay? Now, the question is, how do we consider a parametric version of this hemisphere? And so a parametric version is a vector r, a vector valued function of two variables. Let me say that again. A vector valued function of two variables. It takes in two variables, u and v, and it gives you the coordinates of a point on the surface. So what is that? That's going to be the x coordinate, which is a function of u and v, I hat, plus the y coordinate, which is a function of u and v, j hat, plus the z coordinate, which is a function of u and v, k hat. Each of those is a function of u and v. The x component of your location depends on what thread you're on. What cross thread and cross thread you're on. So that's the u thread and the cross thread v. Okay? So that's what I'm trying to note here. This is, I think I called this u equals constant, and this was a v equals constant thread. Okay? So this is the sphere explicitly z. I want to create a parametrization. As we learned for parameterized curves, there are multiple ways to parameterize the sphere. I'm going to teach you two ways today, or rather, remind you of two ways, because they're actually in your head right now, these two ways. Okay? When we had explicit forms of a curve, we always said that trivial parameterization was available to us. The trivial parameterization was like when I had y in terms of x, I would just let x be the parameter, x equals t. And then you figured out what the equation for y was in terms of t, which was pretty straightforward. In this case, since I have an explicit form, it's actually available to us again to let x equals one of the parameters, and then y could be the other parameter. Okay? Well, why does that work? That works because the hemisphere is a single-valued function, right? The upper hemisphere is a single-valued function over the xy plane. So effectively, that's trivial parameterization, x equals u, y equals v, is really will work. Okay? So let me continue up there. So we do the trivial parametrization. Trivial because it's kind of yelling at you. So x of u and v is equal to u. Y of u and v is equal to v. We had that freedom. We've used the freedom now. Okay? We're stuck. We have no more freedom. Okay? So what do we do now? Well, we use the explicit equation z in terms of x and y and substitute what x is in terms of u and y is in terms of v. So this tells me z of u and v equals the square root of r squared minus u squared minus v squared. And so we write the parameterized form, r of u v is equal to u I hat plus v j hat plus the square root of r squared minus u squared minus v squared k hat. And this is one way to parameterize the sphere, the hemisphere. Okay? Okay. I'm still with the same example. What about another way? What about another way to parameterize the hemisphere? Okay? Let's see what we can do. Well, instead of letting x equals u, maybe I could do something like let x equal u cos v. It's a different way. Remember, u and v are just labels, right, for these threads. Let y equal u times the sine of v. And then when I've used my freedom. It's gone, no more freedom. So z, which is a function of u and v, is equal to the square root of r squared minus this squared plus this squared, which is r squared minus u squared. And then I write my parameterized form, r of u and v is equal to u cos v I hat plus u sine v j hat plus the square root of r squared minus u squared k hat. Now, it's probably sort of, if you jarred your memory, what this is, right? I'm really using polar coordinates in lieu of using Cartesian coordinates in the plane. I'm using polar coordinates in the plane. So I could just write this. Well, why did you write it in terms of u and v, Professor? Why don't you call it phi and little r? So let's call it phi and little r. So wherever I see u here, I'm going to write little r, which is the polar coordinate in the plane. And wherever I see v, I'm going to write phi. And you'll see that this is r cosine phi I hat plus r sine phi j hat plus capital R squared minus little r squared k hat. And this is the parametrization of the hemisphere. This is another parametrization of the hemisphere. This one explicitly uses polar coordinates. Now I used Cartesian coordinates. I used polar coordinates in the plane. Okay? What else could I use here? Well, I could use all sorts of crazy coordinates, right? I could have used any roads that transect, that I draw on the sphere if I wanted to, but they could be very complicated and difficult to analyze. But here is another option. Okay? A third way? Well, I went from Cartesian to polar. We're on the sphere now, right? So let's recall. Let me begin by recalling spherical polar. coordinates. Okay, recall spherical polar coordinates. What are the spherical polar coordinates? This is not the x on the sphere yet. These are just the coordinates right now. Well, I had x is equal to rho times the sine of phi times the cosine of theta. Y equals rho times the sine of phi times the sine of theta. Oops, pause. This, we used theta, right? This is theta. We use theta here. The old brain learned it the other way around. Did I say that already? My old brain, when I was your age, I learned it the other way around. So I make a mess of this all the time. Just call that. It doesn't matter, right? It was consistent nonetheless. But I want that theta to correspond to this theta. This was consistent on its lines, but it wouldn't have been consistent across lines. With my sincerest apologies. Z equals the rho times the cosine of phi. Okay? So any point in space, right? Any point in space is given by either x, y, z, or I can invert this transformation and get rho theta phi for it. Okay? But we see that this is the surface of constant r, of constant distance, right, from the origin. So you can see pretty quickly that, look, the surface is, and I'm going to move over, the surface of constant rho equals r is given by x of theta and phi is equal to capital R times the sine of phi times the cosine of theta. I allow theta and phi to change, but I fix my distance from the origin. Y of theta and phi is equal to capital R. I fix my distance from the origin, also sine phi, times the sine of theta, and z of theta and phi equals capital R times the cosine of phi. Now, since we were working with a hemisphere, we recognize that we have other restrictions here. And another restriction would be, need phi less than pi over 2, less than or equal to pi over 2. Because remember, phi is measured from the North Pole, and pi over 2 would be the equator. Okay, and so you don't want to have negative z's. That makes sense, right? Because when phi equals pi over 2, z equals 0. When phi is greater than pi over 2, z is negative, so we stay away from that. So you can write r of theta and phi. These are the two parameters. And they are going to be capital R, and I'm going to factor out this capital R because it's common to everything. It's nice to factor when you have such a common factor. Sine phi cos theta I hat plus sine phi sine theta j hat plus cos phi k hat. So 1, 2, 3 different ways to parameterize the hemisphere. Okay? But now this kind of like begins to call on, hey, what else could I make with this? What else could I do with this thing, okay? What else could I do with this thing? And I want to focus on spherical coordinates as a way to think of, hey, what else can I do with this? Let's think about spherical coordinates. How do I get the hemisphere from spherical coordinates? Well, I got the hemisphere by setting rho equals constant. Well, what else could I set equals constant? Let's see. How about phi equals constant? So this is now example 2. That was all example 1, because it was 3 different methods of creating the same object, geometrically the same object, a hemisphere. But let's create a different object. Example 2. Let phi equals some fixed phi. Let's call it capital phi 0. It's a number. I want you to think of it as a number. Okay? And what's that? Are you making a cone from that? Say it louder. Would that make a cone? Would that make a cone? Yeah. It would make a cone. Yeah. It's the constant latitude cone, right, that emanates from the origin and goes up. So what is the parameterization for a cone? Well, I use spherical polar coordinates, and I recognize that now that r is a function of the remaining two parameters. It can't be a function of phi, because I fixed phi. I'm choosing a particular cone. So r is going to be a function of distance from the origin and the longitude, theta. And that's going to be rho, I got to do this right. It's going to be rho sine of phi 0, that fixed number, times the cosine of theta, I hat, plus rho sine of phi 0, that fixed number, times the sine of theta, j hat, plus rho times cosine of phi 0, k hat, because that's fixed. So this, what I've done here, is I've used spherical coordinates to parameterize the cone. I've used spherical coordinates to parameterize the cone. You could go on and play this game. It's an important little game. Okay? So, oh, by the way, you can play this game with Cartesian coordinates. You could have done this with Cartesian coordinates. You could write the cone in in Cartesian coordinates, okay? And then said, well, I'm going to solve it for z in terms of x and y, like I did first over here. And let x equal u and y equal v, and do all that. You can figure out what the cone is. Or you can do it in polar coordinates, cylindrical polar, effectively. You can do the whole same thing. So these are examples of what parameterizations yield for you. Okay? You need two parameters because it's a two-dimensional object. And I want you to think of those two parameters as threads, because we haven't done any calculus yet. We have just done a little bit of algebra thus far, and I'm about to do calculus in a second. And I saw a hand up there. Go ahead.
Oh, well, I was going to say, since you switched from R to
Rho.
Rho, yeah. I was going to say, since you switched that into a variable and then phi into a constant, so we need to have, since we made phi a constant, we had to make R a variable.
Right. You need to have two things that vary, right? And you got to think about what there's the two things that vary. But you're on a surface, right? You got to be able to go in two primary directions, right? You got to be able to go into two primary directions. It's a two-dimensional object, so you need two things that vary. Okay? Yes. You fix one, and that's it. Like, think about it. Like, I'm in three-dimensional space, but I've been constrained to be on some surface, right? So I'm in three-dimensional space. I can go in any of three directions, right? But by being constrained, I lose a direction, right? Like in this room, I have to go up that ramp, right? So my z is constrained by my x and y, okay? And so, but two things are allowed to vary. I can go left and right and up and back. Okay? So this is the algebra of it. And if you just think of it carefully, you think about it as threads. Sometimes I ask people to think about the roads of San Francisco, which are crazy, because San Francisco is really a European city, right? It's a city built on a hill, like all European cities are, sort of. But it acts like an American city because it puts a grid on the hill, which is like crazy, right? It goes straight up the hill. Come on. But nonetheless, there's a grid, and you can have the heights, right? But if you go to, like, my dad's hometown in Italy, is like, it's a spiral. It looks like, it goes up the hill like this way, right? That way. So the roads were built differently because we were constrained by the topography. But the roads are the parameterization. They are the u and the v. Okay? I want you to think of those as the u and the v. Okay. So this is a little parameterized surfaces. Now let's do a little bit of calc. Well, I got a surface now. What do I want to know about the surface? Okay? Well, ultimately, we want to know a whole bunch of things about the surface, but we want to be able to do calculus on those surfaces, which means that we need to be able to chop it up into small pieces, calculate the area of those pieces. Okay? We already saw that vector fields and normals are going to be interesting in our study of Green's theorem. So we also don't just need to know about the area of the surface, but it was important to know the orientation. Some surfaces are like this. Some surfaces are like this. We want to know about the surface. And what I'm about to teach you is that knowing R of u and v, which is knowing the global structure of the surface, everything everywhere, we're going to take a couple of derivatives and one cross product, and I will be able to tell you exactly what's going on locally in the surface. Okay? How big are patches of area in the surface, and what is the orientation of the surface? That's what the cross product's going to do. That's what the derivatives are going to do. Okay? So if you can follow me, I'm going to do the geometry of this problem. And we're always going to keep in mind the sphere, because I think the sphere is very, very useful, because we have some experience of living on a sphere. Okay? Okay. So what if I wanted to calculate the area of a surface? What would I do? Well, the prescription is always the same. If one wishes, I mean, you might wish to calculate area of a surface we always chop it into pieces, always chop into pieces, measure area of each piece, and add it up. That's it. What I taught you at the beginning of chapter 15, it applies now. Except there's just a little glitch, right? And the glitch is that these surfaces are curvy things in R3, okay? But I hope you see that they're not that complicated. And now let me draw a small piece. Let me zoom in on the surface, and let me think about one small piece of the surface, okay? So I'm going to draw the thread. This is going to be the thread U equals constant. Okay? And I'm going to let that equal U0, a constant value of the thread, okay? That's the first, maybe that's the first thread right here, okay? And then I'm going to draw the thread V equals constant equals V0. What does that mean? It means that if you were to go along this thread here, V would be increasing because U is constant, but V is increasing. Okay? So here's V equals constant V0. Maybe I'm going to call this one V equals V0 minus delta V, if you don't mind. And then I'm going to go to the next one over here, V equals V0 plus delta V. Delta V is maybe, here's delta V is 1. This is 0th street, 1st street, minus 1st street. Okay? So this is U equals constant, and this will be U equals U0 over there. And then here is this is U equals U0 minus delta U. I'll make it minus in this direction. And then here is U equals U0 plus delta U in that direction. So there's a preferred point here that I'm going to work from is that U0, V0 point. Okay? That's the point on the surface at U0 and V0. So if I were to have a coordinate system, and pardon me, I can't put the coordinate system right there. Here's my coordinate system way over here, x, y, and z. I draw a vector from the origin of x, y, and z to this point. Okay? That is the vector r of U0, U0, comma, V0. That's the vector from the origin to the thread, the cross threads U0 and V0. That's what it means. So that's the vector from here to here. Do y'all see that? Okay. The idea is, I guess I should have said it at the beginning. I suppose that we've been given R of U and V to begin with, okay? We know the global structure. Now we're going to study what's going on locally. Okay. I have drawn this sort of tellingly. I hope I've drawn this tellingly. Okay. What is my chops? My chops here are clearly the delta U chops and the delta V chops, right? Now, there is no reason, a priori reason, that your threads should be intersecting perpendicularly, right? Take a fabric, right, and then stretch it, and you see that they will intersect in some sort of oblique way. When you make it, it's probably perpendicular, but you can make them do all sorts of things. Locally, there's no a priori reason to assume perpendicularity. So locally, they will always look like this. Okay? And what you see is there's a curve from here to here, there's a curve from here to here, there's a curve from here to here, there's a curve from here to here. I want to figure out the area of this patch and the orientation of that patch. Which way is it pointing? I want you to think, by the way, this is not on the board, it's out in space somewhere. It's in three-dimensional space, okay? So it's curved and pointing in some direction. Well, I know the vector from here to here. This is r, that's this one over here, okay? I know the vector, pardon me, I'm going to erase. You've written it in your notes, but allow me to erase right now. I know the vector from here to here, from the origin to here, okay? This is the vector r of u0 plus delta u, because it's on the u0 plus delta u thread, but still on the v0 thread. Okay? Because this is the vector r of u0 comma v0 from here to here. The one nearby is you just increase the delta u thread. And of course, I'm going to, well, of course, I don't know if this is of course, but I hope you see this vector right here is r. I've stayed on u0. I'm still on the u0 thread, but I've gone on the cross thread to v0 plus delta v. These are the three vectors that I need. Why do I need these three vectors? Everybody, in the limit that delta u and delta v get very, very small, this curvy shape is going to look like a parallelogram. Parallelogram. I'm going to need to know what this vector is. I'm going to need to know what this vector is, because those two vectors are the sides of the parallelogram. And you know that the operation to take area is the cross product. So I'm going to know what this vector is. I'm going to know what this vector is. I'm going to take their cross product. And you know that the cross product gives you a vector which is perpendicular to its two inputs, both of its inputs. So it's going to be perpendicular to this one, and it's going to be perpendicular to that one. So it's going to be pointing perpendicular to this plane. That's what I'm going to construct for you right now. So that's the answer, where we're going with the answer, okay? But I'm going to lead you there a little bit on this story. Okay. Let me call this vector from here to here, from the end point to the end point there, I'm going to call that vector A. And I'm going to call this vector vector B. I've drawn it so you see a gap between the curve and A, and you see a gap between the curve and B. Right? It's not exactly the side of this well, this is not exactly a parallelogram. It's not exactly the side of the shape, because the side of the shape is curvy. But we know that that curviness goes away in the limit that delta u and delta v get small. Okay, what is A vector? A vector is equal to, well, look, you go from origin to this point, and then from here to here. That's the same as going from here to here. In other words, A vector is this vector minus this vector. The vector to this point minus the vector to this point. I still, to this day, get my negative signs confused, so I literally have to go tail to head, pause. This plus this equals this. Therefore, this minus this equals, I have to do that, okay? I'm sorry. This old brain gets really atrophied, but if you have to do that, it's okay. I'm giving you permission, okay? So the permission is, hey, look, this is R of u0 plus delta u comma v0. That's A vector. It says, this is R of u0 plus delta u, and this is R, oops, no, it is not. Yellow, wake up. Minus the subtraction. See, I forgot the subtraction already. Minus R of u0 comma v0. Okay? This is functional evaluation here, please. And then B vector, well, you'll see that everything is kind of symmetric, right? This is R of u0 comma v0 plus delta v. That's shifted to this thread over here. So that's the dashed line, which you can barely see, from the origin to this point. And of course, minus the same point, R of u0 comma v0. That's what the vector is. That's what these two vectors are. Okay? Now, folks, whether you love Taylor series or you love the definition of the derivative, or you understand just purely viscerally that those differences are related to the derivative, I'm going to write the following for you. Remember that the derivative of a function with respect to its argument, this is just the good old definition of the derivative, is the limit that delta x goes to 0 of f of x plus delta x minus f of x over delta x. We're going to be doing this for small delta u and delta v. Okay, but I'm going to take the limit at the end. Okay? So instead of having tons of algebra written on the board, I want to point out to you that another way of thinking about this is that delta x, df dx, sorry, is approximately equal to f of x plus delta x minus f of x over delta x for small delta x. I just got rid of the limit, right? But you guys did this on your calculators in 21A where you took the limit by hand. And you made this like 1/1000th and 1/10,000th and 1/1,000,000, whatever. Right? Well, if delta x is small enough, this is approximately true for some small delta x. In other words, if delta x is small enough, I'm going to rearrange this. F of x plus delta x minus f of x is equal to the derivative multiplied by the amount delta x. It's approximate, not equal to. This is approximately equal to. What does this mean graphically, everybody? If you just had a curve x and f of x, you had this curve over here, and you had, this is the value, this is a particular value, say x0, and this is x0 plus delta x, some point down the way. It says, look, the function over here is basically like taking the tangent line of the function, taking the function over here, taking its tangent line, and extrapolating to that point. Okay? That's the tangent line approximation of the function. And of course, that stinks in this case, but in the limit that delta x gets very small, right, it gets better and better and better. That's what this is telling you. Why did I tell you this? Because if you look at that, you recognize that a vector is approximately equal to not the total derivative, but the partial derivative. That's the partial derivative with respect to its first argument. It's equal to dr du evaluated at u0, comma v0 times delta u. If you squint, that's the same, right? A is the difference of r evaluated at a point u0 plus delta u minus r at u0. Well, that's the same thing I'm saying here, which is basically like the tangent line approximation. This is why you did Taylor series. This is why we did calculus in the first place. This is kind of like the understanding of what's going on with any sort of first derivative, with the idea of a limit. Okay? Similarly, b is approximately equal to dr dv of u0, comma v0 delta v. And now we are getting somewhere good. Because, by the way, if you were to do this properly, you would do the whole Taylor series. You have delta u squared, delta u cubed, delta u fourth. You would run the whole Taylor series. You guys would kill me because you don't like Taylor series. I don't believe you like Taylor series. Every time I say Taylor series, people stop making eye contact. They leave the room, right? It's devastating, okay? Taylor series is a wonderful thing, and I encourage you to spend some time with Taylor series, understanding that it is a way to approximate functions. Nonetheless, I'm not going to make you go through the Taylor series limit argument here. Just realize that, hey, nearby, what we're understanding is the change nearby is related to the derivative here multiplied by how far you go. That's what we meant by the tangent line approximation. That's all this is. Okay? Now we've done the calculus. So first I did the algebra by setting up these surfaces. Now I've done calculus by telling you where derivatives pop into this whole problem. And now I just need to do one piece of geometry. Okay? And the geometry is this. If I wanted to calculate the shape of that parallelogram, the parallelogram that comes from A vector and B vector, and then I would do this parallel B vector over here, and this parallel A vector over here. It almost looks like a rectangle. I apologize. These are the sides of that shape. The sides there. Okay? If I wanted to calculate the area of this parallelogram, it is simply area of this parallelogram, just area, is equal to the magnitude of A cross B. That's what the cross product does. It gives you the area between those two vectors. Okay? Remember the definition. This is, just to recall, this is the magnitude of A. I'm not going to write it out. It's the magnitude of A multiplied by the magnitude of B multiplied by the sine of the angle between them. Maybe I'll write it out. Angle multiplied A of B times the sine of the angle between them, where alpha is this angle between them. Notice when alpha is 0, they're parallel. The sine of 0 is 0. There's no area. When alpha is pi over 2, they're perpendicular. That maximizes the area for fixed lengths of A and B. Okay? And when you make them bigger, you make it, you can make that shape thinner again. So the parallelogram goes from thinner to thinner in that direction. Okay, what is this? Well, the area, therefore, I'm going to go to this board. This is a bit of an involved argument, as you see, and I appreciate your dedicated attention to this. I hope it's edifying. So the area, in this case, is equal to dr du cross product dr dv magnitude times delta u times delta v. Because I just put in the delta u and the delta v, they come out of the cross product. They're just a scalar multiple. They're not the common factor to both of these things. So they come out of the cross product. And in the limit, and this is, by the way, evaluated at the point u0 and v0, right? Because that's where those guys were. I'm not going to write it here. But in the limit that delta u goes to 0 and delta v goes to 0, the area goes over to, now when we did this for flat surfaces, we called this dA. Remember that? We called that dA. The D emphasizing a small piece of A for area. But the book, and it's often used in physics also, is we use sigma for this. We use sigma for surface area. So this is going to be used sigma. So the notation is the area goes over into D, small amount of surface area, sigma, Greek letter sigma. Okay? And that's equal to dr du cross dr dv magnitude times du times dv. This is the area of a piece of that surface. So if you know the parameterization, you know how to take its derivatives, you know how to take the cross product, and then you multiply it by the step, delta u and delta v, how many threads you go over in either direction, and that'll give you approximately in the limit the area of that patch. How do you get the area of the whole surface? You do this for all the patches, and you add them up. So the area of the surface equals the double integral over the domain expressed in u and v variables. That's what I mean by this. You express the domain in u and v variables. Right? That would be the limits of integration in the u and v variables. If I use Cartesian parameterization, I would get one thing. If I use polar parameterization, I get another thing. This domain is going to be expressed in u and v variables, whatever those parameters are. And it's going to be the magnitude of dr, du, cross dr, dv, du, dv. And that's how you calculate surface area. when you have that parameterization, this calculation is ridiculously easy to do. Okay? But as my friend told me once, I've left some money on the table. Great analyst. Yeah, hilarious guy. Anyway, for the record, Idris Titi. But Idris says, Joe, you left some money on the table. What did I mean left some money on the table? I took the magnitude. I had a vector, and I took its magnitude. Right? So I lost the information about its direction. What did the directional information give me? Well, the cross product, right? The cross product gives you a vector which is perpendicular to both A and B. That means it is out of the plane. So it tells you the orientation of the plane. Here on this table, if this were A and that were B, that would be pointing up. But on this board, it's pointing out. Why do you care about the orientation of this surface? Well, if it's catching rain, it makes a difference that it's pointing up because the rain is falling down versus pointing horizontally because the rain is falling down and totally missing it. So when we add this to the structure of a vector field, which it may be encountering, its orientation is important. Okay? And so we recognize that the normal vector to the surface, so the normal vector is simply the direction of A cross B. It's simply the direction of A cross B. And so we don't just use d sigma, where d sigma is this infinitesimally small area. We're going to use an oriented d sigma. And so we're going to define d sigma vector. It is the surface area with orientation. And all that means is the unit normal to the surface times d sigma. And all that is equal to is dr du cross dr dv times du, and this is in parentheses, times dv. This is a vector-valued differential. This is the first time you've seen such a vector-valued differential. But this, all I did was get rid of the magnitude. How do I calculate n? Well, to get n hat, I take d sigma and d sigma vector and divide it by d sigma. So what is n hat? It's just, well, you see that the du and dv would cancel out because there's du's, dv's from here and from here. And so n hat is simply dr du cross dr dv. This is a v. This is our vector. This is a v. And that's divided by the magnitude of dr du cross dr dv. It's just the direction of this vector. That's what n hat is. Okay? Now, in the precious few moments I have remaining, I have to obviously continue this on Monday. But let me go back to the sphere, the parameterization of the sphere. Okay? So, e.g. sphere, the hemisphere. Okay? And I'm going to use the theta phi parameterization. Theta and phi, or I don't know if I called it phi and theta before. And this was a sphere of radius r, and what I had was something like sine phi cos theta I hat plus sine phi sine theta j hat plus cos phi k hat. If I recall correctly, that was the parameterization of the sphere. Now, everybody, I want to draw this sphere, and I'm not going to stay with the hemisphere right now. Let's do the whole sphere. Why limit ourselves? Okay? Lines of constant phi are latitude lines. Lines of constant theta are meridians. Okay? Now, this is getting a little busy, but we're at a point here on the surface. If you just give me 2 extra minutes, I'll finish this. We're at a point here on the surface, okay? So let's imagine being at a point phi comma theta on the surface. What is dr d phi. I'm going to calculate it. It's pretty easy calculation. It's r times the cosine of phi times the cosine of theta I hat plus the cosine of phi, the sine of theta j hat, minus the sine of phi k hat. So notice dr d phi is, well, this is vector. You're like, I can't evaluate that in 10 seconds, Professor. What are you doing to me, okay? Well, just know what we meant by it. Dr d phi is the amount that r changes as you increase phi. Phi means you're going further south. If you increase phi, you're going further south. So it's a vector pointing this way. Ta-da! We have another name for this vector. It's called south. This vector is south. South with some magnitude. Okay? And it says how much, if you go 1 radian or 1 degree, like one amount of delta phi south, how much distance have you traveled? How much r have you traveled? R vector have you traveled? Where has your r vector gone to? That's south. What's dr d theta? Well, it says if I were to increase my theta, how much does my r change if I increase my theta? What's the name of dr d theta? What name would I give it? East. So east, so by the way, notice that south is pointing in the negative k hat direction, because sine phi is always positive. So it's going south. There's the southiness. Okay, east is r sine phi, negative sine phi, sine theta I hat, plus sine phi cos theta j hat, plus 0 k hat. Because east, you don't change your z direction. You're going on a constant latitude circle. So you're not changing your z direction. This is south, this is east. Now, watch. Just watch for 1 second. South cross east is up. Up, because up is out of the sphere. South cross east is up. Okay? I'd like you to do that cross product at home.